Hello. If you know about limits in calculus, either because you've watched my other videos on limits or you've studied them elsewhere, you know that the limit of a function as x approaches some particular number is all about what happens to that function when x is close to, but not equal to, that number. Now, if you're talking about real numbers, which we are in a beginning calculus class, there are two ways that you can be close to a number. One way is by being a little bit less than that number, and the other way is by being a little bit greater than that number. And for regular ordinary limits, we need to consider both sides, both ways of being close to a number. But there are some times when we only want to consider one side. We only care about what happens when we're a little bit less than a number, or we only care about what happens when we're a little bit greater than that number. And that's when we use one-sided limits. Now, there are two reasons why we might need to do that. One reason is that there are some functions that are only defined on one side or the other of a particular number. For example, the square root function is only defined when x is greater than or equal to 0, at least as long as we're working with the real numbers. So you couldn't talk about what happens to this function for all x close to 0, only for the x's that are close to but greater than 0. The other reason we might want to consider one-sided limits is if something completely different happens on either side of a number. We have one thing happening when x is a little bit less than that number, and something completely different happening when x is greater than that number. Here's an example of where that happens. This is the function that takes whatever number you give it for x and takes the absolute value of that number divided by that number itself. So if the number you put in for x is positive, if it's even a little tiny bit greater than 0, then the absolute value of x is the same as just x itself, and when you divide, you get 1. On the other hand, if x is a negative number, even a little tiny bit less than 0, then the absolute value of x is positive. And so the absolute value of x and x itself are opposites of one another. One's positive, one's negative, and when you divide, you get -1. So we have different things happening on different sides of where x is 0. Now, if you remember my previous videos, or if you've studied limits, and you've seen either the informal or the formal definition of a limit, part of the background, the conditions behind that definition is that the function has to be defined for all x close to the number it's approaching. F of c may or may not be defined, but f of x is defined for all other x near c, or for all x in some interval containing c, except possibly at c itself. So these definitions don't really work. They don't really apply in situations where the function is not defined for all x close to c. But if you do have a function that's defined for all x just on one side or the other, you can still talk about one-sided limits. So if I write lim, and then under that put x, and the approaching arrow, and then a number, and then put a minus sign after that number. So the minus sign is not in front of the number, like it's -c. It's after that number, so it's c, and then a minus sign after that. That's how we write the limit as x approaches the number c from the left. So that's all about what happens when x is close to but less than the number c. The limit as x approaches c from the left of f of x is the number that f of x is close to whenever x is close to but less than c. And some people call this the limit as x approaches c from below. It's just different ways of looking at it horizontally versus vertically. If you have your number line arranged horizontally, then numbers that are less than 3, for example, would be the numbers that are to the left of 3 on the number line. So if you're approaching 3 from the left, you're looking at the part of the number line where the numbers are less than c. But if it's arranged vertically, then the numbers that are less than c are the ones that are below that number. So if you're approaching 3 from below, you're looking at the numbers that are less than c. And since the number that's doing the approaching is the independent variable that we're plugging in for x or whatever, and that is usually graphed on the horizontal axis, I think it makes more sense to talk about approaching from the left. But I have seen people and books that talk about approaching from below. So here's an example. Here the function f of x is the square root of 4 minus x. And if x were any greater than 4, then 4 minus x would be negative and we wouldn't be able to take the square root. So this is only defined when x is less than or equal to 4. So we can't really talk about just the limit as x approaches 4, but we can talk about the limit as x approaches 4 from the left. And that limit turns out to be 0, because when x is close to 4, 4 minus x would be close to 4 minus 4, which is 0. And so the square root of that would be close to the square root of 0, which is 0. And you can see that on the graph. The points on the graph with x coordinates that are close to, but just a little bit less than 4, all have y coordinates that are close to 0. Then the limit as x approaches c from the right, where we put a plus sign after the number that x is approaching. The limit as x approaches c from the right means what f of x is close to whenever x is close to but greater than c. And it's most common to say from the right, but some people say from above. X is approaching from above. So an example of this would be, going back to just the square root of x, we can say the limit as x approaches 0 from the right of f of x is 0. When x is close to but a little bit greater than 0, the square root of x is close to 0. And going back to this function, we can say that the limit of this function, the absolute value of x divided by x itself, as x approaches 0 from the left, the limit is -1. And the limit as x approaches 0 from the right is +1. The points on the graph with x coordinates just a little bit less than 0 have y coordinates close to, in fact equal to, -1. And the points on the graph that have x coordinates that are close to but greater than 0 have y coordinates up here at +1. Now, if you are familiar with the formal delta epsilon definition of the limit, you might want to think about how you would adapt that definition to just talk about one-sided limits. If you're not familiar with that definition, or you don't care about that, you have my permission to skip this. You can fast forward or zone out during this next minute or two when I'm talking about this, and come back when the screen goes from blue back to white. But if you are interested in this, here to remind you is the formal mathematical definition of what it means to have the limit as x approaches c of f of x be the number L. So to change that so that we only talk about the limit as x approaches c from the right, Now, we don't have to have f of x defined for all x in some interval containing c, except possibly c itself. We only have to have f of x defined when x is greater than c. So we can say, suppose f of x is defined for all x in some interval from c to some other number b. So that's the numbers that are greater than c. And then instead of the absolute value of f of x minus L being less than epsilon, that is, f of x being close to the number L, within epsilon of L, whenever x is close to c, now it's whenever x is close to c and greater than c. So we can write it like this, or we can write it more compactly. Instead of specifying, okay, x has to be greater than c and 0 is less than the absolute value of x minus c is less than delta, we could just say that x minus c itself, without the absolute value bars, is greater than 0, which ensures that x is greater than c, and is less than delta. So this would be the official formal definition of what it means to have the limit of f of x as x approaches c from the right be the number L. Then for the limit as x approaches c from the left, we would need f of x to be defined to the left of c, like for some interval from a to c. And then we would want the absolute value of f of x minus L to be less than epsilon whenever x was less than c, so c minus x being greater than 0. If x is less than c, then c is greater than x, and c minus x is greater than 0, but it's still less than delta. Okay, so if you were zoning out, you can come back and now look at some examples, some more examples of one-sided limits. Here we have the function f of x equals 6 over 2 plus e to the 1 over x. Here's what the graph looks like, and you'll notice the graph is in two separate pieces. This function would be undefined at 0, because if x is 0, 1 over x would be undefined, and so right there it breaks down. But the limit as x approaches 0 from the left is 3. You should be able to see that on the graph. Look at the part of the graph where x is less than 0. And as x gets closer and closer to 0, but from the left, the y-coordinates sure look like they're getting close to 3. Now, what about the limit as x approaches 0 from the right? That would be this part of the graph where the x's are greater than 0, and on this part of the graph, as x approaches 0 from the right, the y-coordinates are getting close to 0. And so the limit as x approaches 0 from the right of f of x is 0. Now, if we just said the limit as x approaches 0 without specifying the left or the right, that limit just does not exist. And that's because there's no one particular value that f of x is always close to for all x close to 0. For some x close to 0, f of x is close to 3. And for other x close to 0, f of x is close to 0. Like if you want to look at some particular examples, plug in negative 0.1. There's an example of a number that's a little bit less than 0, and you get a value of 2.99993 approximately, close to 3. Plug in a number that's a little bit greater than 0, like positive 0.1, and you get a value like positive 0.00027, close to 0. But those two numbers aren't very close to one another, and so we have this big gap here, this big jump from one level to another. And so the limit just as x approaches 0 does not exist. And we can take it as a theorem or a fact that can be proved that the limit as x approaches c exists if and only if the limit as x approaches c from the left and the limit as x approaches c from the right both exist and are equal to one another. So if these two one-sided limits were the same as each other, that would be the limit just as x approaches 0. But since they are different from one another, that's enough to tell us that the limit just as x approaches c, in this case 0, does not exist. So if the two one-sided limits are different, the regular limit, doesn't exist. If the two one-sided limits are the same, they're both the same number, so they both exist and agree with one another, then the limit, just the regular limit, does exist, and it is that same number. Here's an example of a function that's defined in two pieces. So what this function does to your x depends on what that x is. If that x is greater than or equal to 0, it gives you the square root of x. On the other hand, if the number you put in for x is less than 0, that is, if it's a negative number, then first this function takes minus x, takes the opposite of that negative number, which would be positive. Then it takes the square root of that, and then it makes it negative again. So like, for example, if the number you put in were negative 9, so if x is negative 9, then minus x would be positive 9. The square root of positive 9 would be 3, and then we have negative 3 as the value of the function. So put in a positive number, we get its positive square root. Put in a negative number, we get the negative square root of basically its absolute value. So what happens as x approaches 0 from the left? X approaching 0 from the left means we only care about x's that are less than 0. So we're only focusing on this part of the definition. And as x gets close to 0, this x here getting close to 0 means that minus x is getting close to 0. The square root of that is getting close to the square root of 0, which is 0. And minus that is approaching minus 0, which is 0. So that limit is 0. Now what about the limit as x approaches 0 from the right? So now we're considering x's that are greater than 0. So we're only looking at this part of the definition, where whatever we put in for x, what we get out is the square root of that number. And as x approaches 0, as x gets closer and closer to 0, the square root of x is approaching the square root of 0, which is 0. So that's that limit. And since we have the same thing on both sides, the limit as x approaches 0 from the left and the limit as x approaches 0 from the right are both 0, that's what the regular limit is. The limit just as x approaches 0 is 0. And here's what the graph looks like. I wanted you to be able to understand the limit without having the graph to look at, but now that we know what this is, hopefully you can see that on the graph, how if x is a little bit less than 0, the y-coordinates are close to 0. And if x is a little bit greater than 0, the y-coordinates are also close to 0. We're approaching 0 from both sides. Here's another function that's also defined in two separate pieces. Here f of x is x plus 2 if x is a number less than or equal to 3, or it's 5 minus x if x is greater than 3. So what's the limit as x approaches 3 from the left? Which part of the definition are we looking at? The part that applies when x is less than 3. That's the top part. So as long as we only look at x's that are less than 3, what we're getting out of the function is x plus 2. And as x approaches 3, that would be approaching 3 plus 2, which is 5. So the limit as x approaches 3 from the left is 5. Now what about the limit as x approaches 3 from the right? What are we looking at now? Now we're considering the x's that are greater than 3, so we only care about this second part of the definition. as long as x is greater than 3, what we get out of the function is 5 minus whatever x is. And as that x is approaching 3, 5 minus x would be approaching 5 minus 3, which is 2. So the limit as x approaches 3 from the right is 2. And what does that tell us about the limit just as x approaches 3? It's 5 from the left, it's 2 from the right, and since it's different things on different sides, the limit just as x approaches 3 does not exist. Here's the graph. Hopefully you can see as x approaches 3 from the left, the limit is 5. And as x approaches 3 from the right, the limit is 2. And we have this big gap here, something that's called a jump discontinuity, where the two pieces do not match up. And so for some of the x's close to 3, we have one thing, and for other x's close to 3, we have something completely different. So there's not just one thing that f of x, or y, is always close to for all the x's that are close to 3. That's why the limit, just plain old x approaching 3, does not exist. Okay, and what about the greatest integer function? This is the function that takes whatever number you give it and rounds it down to the greatest integer that is less than or equal to x. So if the number you put in for x is already an integer, you just get that same number out. But if it's not an integer, it gets rounded down to the nearest integer that's less than or equal to the number you put in. So if the number you put in is like 3.1 or 3.8 or 3.625 or pi, which is 3.14159 and so on, if it's anywhere greater than 3 but still less than 4, this function rounds it down to 3. And here's what the graph looks like. Now, what's the limit of this function as x approaches 2 from the left? That means we're thinking about x's that are less than 2. And as long as x is even a little bit less than 2, like think something like 1.99, what do you get out of the function? You get that number rounded down to 1. So no matter how close x gets to 2, as long as x is less than 2, f of x is close to, and in fact equal to, 1. So that's the limit as x approaches 2 from the left. What about the limit as x approaches 2 from the right? Now we're looking at x's that are greater than 2. Maybe just a little tiny bit greater, but still greater. Things like 2.01, and this function would round those down to 2, so that would be the limit. The limit as x approaches 2 from the right is 2. And since it's one thing on the left and a different thing on the right, what does that tell you about the limit just as x approaches 2? It does not exist. So that's one-sided limits. Hopefully that's a pretty easy and straightforward and concept that makes sense. Thanks for watching.